Consider the relation between two integers m and n, where m is a multiple of n. Determine whether this relation is symmetric, reflexive, and transitive. Let's try to understand the problem first. So here we have two integers, m and m is going to be a multiple of n. Now, in order to show that this relation is symmetric, reflexive, and transitive, let's try to define the relation R. So here we will consider that let R be the relation. Let R be the relation on the set of integers z defined by, we could say defined as, we have R being a set of the ordered pairs m comma n such that m is a multiple of n. Now m being a multiple of n, it's the same way of saying that n divides m, right? So what are m and n? So here m and n are both integers. Okay, so this is our relation, and we need to show that this particular relation is symmetric, reflexive, and transitive or not. Okay, let's quickly go through the definition, what it means when we say a relation is symmetric, reflexive, and transitive. So a relation R on the set A is said to be reflexive if and only if we have the ordered pair A comma A belonging to the relation R for all values of A belonging to the set A. Then R is going to be symmetric if the ordered pair A comma B belonging to the relation R would imply that the ordered pair B comma A also belongs to the relation R for all A comma B belonging to the set A. And then number 3, R is going to be transitive if we have the ordered pair A comma B and the ordered pair B comma C belonging to R would imply that the ordered pair A comma C also belongs to the relation R for all A, B and C belonging to the set A. Let's start with the first one. Let's check whether if our given relation R, this is reflexive or not. For this, what we'll do, we're going to consider an element. So let's say that the element is x, that x belongs to the set of integer and x is going to be an arbitrary element, such that if we consider the ordered pair x comma x belonging to the relation R, this should mean that x divides x. Right. Now, does x divide? Yes, definitely. X is definitely going to divide x. That is a true statement. So here we can say that R is reflexive. We have checked that if R is reflexive or not. Yes, it is indeed a reflexive relation. All we have done here is we have the original definition for R as the set of ordered pairs m comma n. So to show that R is reflexive, where we have considered m and n to be equals to x. Then in that case, we have obtained that x indeed divides x. Okay, now R is reflexive. Let's go to the second one and check whether if it is symmetric or not. Now to check for symmetry, we'll have to consider two elements. Let's say x and y be those two elements. These are two arbitrary elements that belong to the set of integers, such that if we consider the ordered pair x comma y belonging to the relation R, this would mean, that means we have y dividing x. Then y must divide x. We're using the definition here. Y must divide x. Now, if y divide x, in other words, all we are saying that x is a multiple of y. So x is a multiple of y means x will be equals to lambda times y. We can say that where we have considered lambda to be some integers. Now, what we can do, we can rewrite this equation as y equals to 1 over lambda multiplied to x. Now there is a problem. Now 1 over lambda, that is not an integer. So that is not an integer, so we have a problem. We cannot say for sure that y is a multiple of x. So we cannot say that y is a multiple of x. Y is not a multiple of x. Y is not a multiple of x. Now since we cannot say that y is not a multiple of x, so here it means that the ordered pair, this simply implies that the ordered pair y comma x does not belong to the relation R. We could think of this in this particular fashion. So let's say we consider the ordered pair 4 comma 2, right? So if we have 4 comma 2, now clearly this means that this simply, if we say that this belongs to the relation R, this simply means that 2 divides 4. That's true, 2 indeed divides 4, but 4 does not divide 2. 4 does not divide 2. So since 4 does not divide 2, this simply is telling us that 2 comma 4 does not belong to the relation R. So here in this particular case, we have shown that the relation R is not symmetric. This is not a symmetric relation. Not a symmetric relation. Fine. Next, we are going to check whether if our relation R is transitive. So here we need two ordered pairs. So let's say we consider three elements. Let's say those three elements be X, Y, and Z. And let us suppose that all of these are belong to the set of integers Z. Then, if we consider the ordered pair X, Y belonging to the relation R and Y, Z belonging to the relation R, our goal will be to show that X, Z also belongs to the relation R. In other words, what we have to show here that Z divides X. So let's say if it is true or not. Now if X, Y, the ordered pair belongs to R, then according to the definition we have Y dividing X. And Y, Z belonging to R simply means that Z divides Y. Okay, so Y divides X is the same as saying X equals to let's call it lambda times Y. That means X is a multiple of Y. And Z dividing Y means Y is a multiple of Z. So let's call it beta times Z. Okay, so where we have to specify where lambda and beta are some integers. Okay, now our goal is to show that Z divides X. So what we will do, so from here let's isolate Y from here. So Y is going to be X over lambda. We're going to substitute Y with X over lambda into this equation. So we get X over lambda equals to beta times Z. So X is going to be equals to lambda times beta multiplied to Z. Now lambda and beta being integers, the product is also going to be an integer. So here we have showed that X is a multiple of Z. In other words, we have showed that the ordered pair X, Z belongs to the relation R as well. So we have successfully shown here that if the ordered pair X, Y and Y, Z belongs to R, then X, Z is definitely going to belong to the relation R. So here we can say, so our given relation R is transitive. So our relation R is transitive. So here in this problem, so which is defined where M and N are integers such that M is a multiple of N, the relation is going to be reflexive and transitive, but it is not going to be symmetric.